Dear students, in the previous lecture I have explained about economic order quantity. So, in this lecture I am going to explain another inventory model, that is called economic production lot size model. So, the agenda for this lecture is I am going to explain what is economic production lot size, then I am going to derive an expression for the total cost. So, from that total cost expression I am going to find out the optimal, that is economic production quantity. Lot size means here quantity. So, I have taken two sample problems, then I will solve these two problems. So, economic production lot size model. The inventory model presented in this lecture is similar to EOQ model, in that we are attempting to determine how much we should order and when the order should be placed. This problem is taken from the book Anderson et al. So, in this model also, economic production lot size model also, we are assuming a constant demand rate. So, instead of assuming that the order arrives in a shipment of size q star as in the EOQ model, we assume that the units are supplied to inventory at a constant rate over several days or several weeks. So, what is the meaning? In the previous EOQ model we have assumed this way, but now what we are going to assume that it is not going to come at a time. So, first we are going to build the inventory, okay, then after that we are going to utilize that inventory. Okay. So, the constant supply rate, okay. So, after producing we are going to supply, the constant supply rate assumption implies that same number of unit is supplied to inventory each period of time. How we are able to supply? After the production. This model is designed for production situations for which once an order is placed, production begins and a constant number of unit is added to inventory each day until the production run has been completed. The lot size is the number of unit in an order. So, it is like this. So, we received a order. So, we keep on building inventory by production. So, here what is lot size is the number of units in an order. So, this model only applies to situation where the production rate is greater than the demand rate. That is one assumption. What is that? So, we are producing more than the demand. So, production rate is greater than the demand rate. So, the production system must be able to satisfy demand, that is why we are having this assumption, production is more than the demand. Here the holding cost is identical to the definition of EOQ model, but the interpretation of ordering cost is slightly different. Holding cost is similar to EOQ, but the interpretation of ordering cost, we are going to use another name for this ordering cost. So, that ordering cost is nothing but the setup cost. Here the ordering cost is more correctly referred to as the production setup cost. So, every time when we are preparing for the production, there is a setup costs we have to incur. So, that cost is equivalent to our ordering cost. What is setup cost? This cost, which includes labor, materials and the last production cost incurred while preparing the production system. Whenever we receive the order, we have to prepare the production system. For that there are a certain amount of cost is incurred. So, that cost is setup cost. So, preparing the production system for operation is a fixed cost that occurs for every production run regardless of the production lot size. So, the inventory pattern for the production lot size inventory model is like this. You see, in x axis there is a time is there, in y axis we are building the inventory. Okay. So, that is the production phase, and once it reaches the maximum level of inventory, again we are stopping the production, there is a consumption is taking place, non production phase. So, the average inventory is this dotted line says the average inventory. First you will derive the total cost. Let us begin building the production lot size model by writing the holding cost in terms of production lot size Q. Again the approach is to develop an expression for an average inventory, then establish the holding cost associated with average inventory. So, first we are going to find out what is average inventory, then we are going to multiply by holding cost, so that we will get average inventory holding cost. The constant inventory buildup rate occurs during the production run. So, during this time, see that during the production time the inventory buildup is taking place. A constant depletion rate occurs during the non-production period. So, during non-production time we are consuming the inventory. So, the average inventory will be one half of the maximum inventory. Suppose this is the maximum inventory. So, half of this, similar to what we have done in the EOQ model. So, one half of the maximum inventory is the average inventory. So, in this inventory system the production lot size Q does not go into the inventory at one point in time. You see that it is not the vertical line, it is keep on increasing, and thus the inventory never reaches level of Q units, because since the consumption also taking place simultaneously. So, the inventory level never reaches level of Q units. Now, we will derive the expression for total cost. Let D represents daily demand rate, P represents daily production rate, and T represents number of days for a production run. Because we are assuming that the daily production rate P will be larger than daily demand rate. So, the daily inventory buildup rate during the production phase is P minus D. So, during the production phase the inventory buildup is P minus D. So, when we can reach, when the inventory will become maximum, so the maximum inventory is this T. So, duration and multiplied by T. So, the maximum inventory is P minus D multiplied by T. Now, we are going to get an expression for the T. How? We are producing a production lot size of Q units at a daily production rate of small p units. Then the lot size Q is equal to per day production multiplied by number of days. Okay. Then the length of the production run T, okay, must be, so Q upon P. What is a Q? Q is the lot size, small p is per day production rate. So, we are going to substitute the value of T into our maximum inventory formula. So, maximum inventory formula P minus D multiplied by T, instead of T we are substituting Q upon P. So, when we simplify this, you will get 1 minus D by P and multiply by Q. Previously we got the expression for maximum inventory. Now, the average inventory is one half of the maximum inventory. So, the previous expression we are going to divide by 2. So, 1 by 2 multiplied by 1 minus D by P into Q. So, when you multiply this average inventory by annual inventory holding cost, so we will be getting annual inventory holding cost. What is that? Average inventory. This expression is average inventory. Then CH is annual inventory holding cost per unit. Now, we will find the annual setup cost and the annual total cost. If capital D is the annual demand for the product and C naught is the setup cost, okay. See, previously we are used this notation C naught for the ordering cost. Here C naught is the setup cost for production run. Then the annual setup cost is as follows. How? Number of production runs per year multiplied by setup cost. So, what will be the number of order? It is similar to number of orders, demand divided by lot size, that will be number of production run multiplied by setup cost per production run. So, now we have the expression for this one for the inventory holding cost, this one is for our setup cost. So, here we have to find the value of Q that minimizes the total cost. Suppose the production facility operates 250 days per year, then we can write the daily demand D in terms of annual demand D, capital D, as follows. In fact, what we are trying to do, we are going to because we have written 1 minus D by P, small p. So, this is Q and CH, for example, here CH. Here the D is the per day demand, P is per day production. So, we are going to get the annual demand here. So, we are going to replace the small d upon P by capital D upon capital P. That is what we are going to do. So, small d is per day demand is annual demand divided by number of working days. Okay. Let capital P denotes the annual production for the product. If the production were produced every day. So, what will be the annual production? Will be 250 multiplied by small p, that will be annual production. So, from this expression we can get the per day production. So, we got per day demand, per day production. So, instead D by P, when you substitute, we are getting the expression. So, these 250 number of working days is not important. So, what I am saying, the ratio of per day demand and per day production equal to annual demand upon annual production, capital P. So, this ratio is same. Okay. So, in our total cost formula, we are going to use this annual demand and annual production. So, what we have done? So, we have rewritten that instead of small d by P, we have written capital D by P. The above used formula is more frequently used because the annual cost model tends to make the analyst think in terms of collecting annual demand data and annual production data P rather than daily data. Now, we have to get the value of Q. So, we could use the trial and error approach to compute the total annual cost for various production lot size Q. However, the trial and error is not necessary. So, we can use the minimum cost formula Q star that has been developed using differential calculus. We know that already what is the condition for minimum and maximum, this I have already explained also. So, if you want to know, say this is minimum, so what is the condition? dy by dx equal to 0 and d square y by dx square. If it is positive, that means the point after solving dy of dx equal to 0, you will get the minimum point. Okay. That is what we are going to do, but here we have the expression in terms of Q. So, development of the optimal lot size Q star formula for the production lot size model. We got the total cost expression 1 by 2 1 minus d by P QCH plus d by QC naught. This we can solve by using nonlinear method also, but we can use it, we can derive using the minimum principle. So, we can find the order quantity Q that minimizes the total cost by setting the derivatives. So, what we are going to do, this expression we are going to differentiate with respect to Q and equate it to 0, then we are going to get the value of Q. So, if I differentiate this, the first term it will become 1 because the Q. So, 1 by 2 1 minus d upon p c h. So, the differentiation of 1 by Q is minus 1 by Q square. Okay. So, then equated to 0. So, I am getting this expression 1 by 2 1 minus d by p c h equal to d by Q square equal to C naught. So, when I rearrange this, so the Q square is 2 d C naught 1 minus d by p multiplied by holding cost. So, if you want to know the, because it is square, you will take square root, you will get the Q star. The Q star is our ordering quantity 2 d C naught 1 minus d upon p C h. The second derivative, you say it is a positive, that implies that this point is the minimum point. So, what expression we got here? 2 d C naught upon 1 minus d by p multiplied by C h. Here C naught is the setup cost, C h is the holding cost, capital D is the annual demand, capital P is the annual production level, Q star is economic production quantity. Now, what is the connection between EOQ and EPQ? So, EOQ formula, what is the EOQ formula? EOQ 2 d C naught by C h square root. Now, what is the economic production lot size formula? Economic production lot size or economic production quantity, say. So, 2 d C naught 1 minus d upon capital P multiplied by C h. So, what will happen as the production rate P approaches infinity? If this P value approaches infinity, so this ratio becomes 0. So, there is a square root. So, this ratio becomes 0, then it will become 2 d C naught by C h. So, when the production rate approaches infinity, the formula for economic order quantity and economic production quantity are same. Now, we will take one sample problem, then we can find the economic production lot size. So, as a company is producing soap, a soap is produced on the production line that has an annual capacity of 60,000 cases. The annual demand is estimated 26,000 with the demand rate essentially constant throughout the year. The cleaning, preparation and setup for the production line cost approximately $135. So, this $135 is our setup cost. So, the manufacturing cost per case is $4.5 and the annual holding cost we got 24%. So, holding cost is interest rate multiplied by unit. So, what will happen? $4.5 multiplied by 0.24. So, the annual holding cost is $1.08. Now, what is the recommended production lot size? So, the demand is given 26,000, ordering cost is given $135 and the production capacity also given 60,000. All the values are given here. So, when you substitute, we are getting Q star, that is 3,387, that is our economic lot size, the otherwise production lot size. So, now we got the Q value. When you substitute into the total cost expressions, we are getting, so Q I have substituted 3387, here also. So, I am getting 2073. See, the total annual cost, okay, if you follow this lot size 3387, the annual cost is $2,073. Suppose some more informations are given. What are they? A 5-day lead time to schedule and set up a production run and 250 working days per year. So, this information also given. What are they? Lead time is given and the number of working days per year also given. So, by using this information we are going to find out the reorder point. So, first we will find out the lead time demand. So, what is the lead time demand? Per day demand multiplied by the lead time. Lead time is 5, annual demand is 26,000, number of working days is 250. So, you will get the per day demand. So, when you multiply number of lead time you will get to 520 cases. So, the reorder point is 520 cases. Now, we are going to find out the cycle time. It is similar to what we have done in economic order quantity. So, number of setup. So, how we will get the number of setup? Number of setup is D upon Q star. So, this value, so we have to know what is the total number of working days, 250. So, when you divide 250 divided by number of productions, that is D upon Q star. So, it will become 250 Q star upon D. So, it is 33 days. So, what the 33 days says? We should plan a production run 3,387 units every 33 working days. So, this duration is 33. So, the Q value, the Q, that is optimal production quantity, is 3,387. So, the reorder point, is when it reaches 520 units, okay. Then we, here reorder means, what is the meaning of reorder point? When it reaches 520 units inventory level, you should get ready for the production. We can take another problem to understand this concept. So, a publishing company produces books for the retail market. So, the demand for the book is expected to occur at a constant annual rate of 7,200 copies. So, here the 7,200 is your capital D. The cost of one copy of the book is $14.5. The holding cost is based on 18% annual rate. So, with this information we can find out annual holding cost. What is that? Interest rate multiplied by the unit cost. What is the interest rate? 0.18% multiplied by 14.50, that will be the annual inventory holding cost. Then setup cost. Setup cost is $150. The equipment with which the book is produced has the annual production volume of 25,000 copies. So, this capital P is annual production is 25,000 copies. That publishing company has 250 working days per year and the lead time for the production run is 15 days. So, lead time is given. So, number of working days also given. So, what we have to find out? Minimum cost production lot size Q star we have to find out, number of production runs per year and cycle time, length of the production run, maximum inventory and total annual cost and reorder point. So, in our lot size model, so y axis is inventory So, this is where our production run is taking place. After that the consumption is taking place. So, we have to find out Q star and number of production runs, cycle time, length of production run and so on. First we will find out the production run. So, Q star is 2D C naught 1 minus D upon P multiplied by CH. The annual demand is given 7200, ordering cost also given, the production capacity also given. So, 7200 upon 25,000. Then you see that we are finding the annual holding cost. So, this 1078.12 is the optimal production quantity, sir, otherwise optimal lot size. The second question is number of production run. So, we know that the annual demand is 7200. So, when you divide that one by number of production runs, so there should be 6.68 production run. And what is the cycle time? The cycle time is number of working days divided by number of production runs, that is D by Q. So, when you simplify it will be 250 Q star by D. So, this is 37.43. That is our cycle time. Then the production run length. You see the cycle time is this much distance. So, this much distance is our cycle time, say capital T. So, in this the small t is this much distance where the production run is taking place, that is a production run length. So, how we are finding the production run length? So, we know this already we have derived an expression Q equal to per day production multiplied by small t. This t is our production run. So, the Q is given, Q is 1078 and the annual production rate is given. So, when you divide this annual production rate by number of working days, we will get the per day production run. Okay. So, from this expression if you want to know the T, so it is Q upon per day production run. So, that is 10.78 days. What is the maximum inventory? Maximum inventory, we had this expression 1 minus D upon P multiplied by Q. So, this point is maximum inventory, this point. So, that is 767. Okay. Holding cost is 1 minus capital D by P multiplied by 1 by 2 into Q and CH. 1 by 2. So, annual demand, annual production rate, Q and the holding cost, annual holding per unit annual holding cost. So, you will get $1,001.74 is the annual holding cost. So, here ordering cost is equivalent to number total setup cost. So, number of setup D by Q multiplied by setup cost. So, ordering cost is 1001. So, the holding cost is 1001.74 and the ordering cost is 1001.74. So, the total cost is $2003.48. Next we are going to find out the reorder point. So, reorder point is per day demand multiplied by lead time. So, per day demand is 7200 upon 250. So, lead time is 15 days. So, when you multiply we will be getting 4032. So, in this lecture I have explained economic production lot size model. I have derived the formula for economic production lot size model. Then I have derived an expression for the total cost also. Then I have taken 2 problems, then I have solved that problem to understand the concepts. Thank you very much.